you see my slides? Okay. So hello everyone. My name is Qingjin Chen. Actually, I just graduated from Columbia. I'm actually a postdoc at Yale. I'm joining Duke ECE in the next fall. And today I'm going to do some of these wireless and SDR tutorials as part of the Cosmos tutorial. And here's the outline of what we're going to do today. So in the first part, we'll go through some of the basics of CISO and MIMO channel sounding. So this will be done in Cosmos Sandbox 2, which you can see in my background. We'll be doing the experiments first in the sub-6 gigahertz. And then after the break, we'll do a similar thing here using the CISO channel sounder framework. We'll apply that to the 28 gigahertz phased array antenna module, which recently got from IBM as part of the Cosmos testbed. So the idea is that we'll be running some of these tutorials here in Sandbox 2, but eventually you're welcome to try out these tutorials using other nodes, both indoor and outdoor deployments in Cosmos. And hopefully once we have more millimeter wave radios deployed outdoors, we can actually take these examples outdoor and then do some real channel measurement and some other related experiments. So just very brief, here's the Cosmos Sandbox, which you can also see from my background. So essentially, we have two USRP 2974s. So these are the two, actually turn on my spotlight. So these are the two blue radios here. And we have two USRP N310s. So these are the two gray radios here. And we have a bunch of RF front ends, including antennas and RF switch boxes, which are interconnected between the antennas and the SDRs. We also have two photoplex front end, which are customized and made at Columbia as part of our Flexicon project. And Manav will be speaking about the example on photoplex wireless in the next part. And you can also see from my background, there are two beta versions of the IBM phased array antenna module, which we just integrated in the Sandbox 2. And we'll be running the channel sounding tutorial with these 28 gigahertz phased array antenna modules after the coffee break as well. And something you don't see from this figure is a bunch of servers located in Columbia Data Center, which are interconnected with the radio nodes through the top of rack switch and data plane switch using these fiber pairs. You can see, in the background there's a bunch of fiber pairs, and there's a patch panel in our lab that connects all the fiber pairs between the radio nodes and the servers located in Columbia Data Center. And within this Sandbox 2 mini rack, you can also see a bunch of other stuff, including the top of rack switch, the power management unit, which allows users to turn on and off the radio nodes and the RF front ends from remote, and the optical mux, which allows different radios to share the same fiber pair to the data center servers. So let's get started with the CISO channel sounding. So this is actually using the real-time sounder framework written in C++, developed by the Renew project. So this kind of shows the synergy between the two power testbeds in the current status. So essentially, this is a C++ based real-time sounding framework that supports TDD operation. So I'm just going to go through the concept and how this works very quickly. So let's say you have two radios in the CISO setting. So let's say the base station has one antenna and the client has one antenna as well. And we want to perform CISO channel sounding in the uplink. So how it works is basically that the base station keeps broadcasting beacons on the downlink, and the clients will start to look for the beacons by doing the synchronization with the beacon sequence. And once the client is synchronized with the beacon, it's going to schedule its upcoming uplink pilot and uplink data transmissions. And since the client is synchronized with the base station knows which slots it should be hearing the received pilot on uplink or the received data package from the uplink. So essentially, this functionality was implemented in C++ as part of the Renew project. So this was developed for the Iris radios as part of the Powder Renew testbed. So here, from our side, we added the UHD support to this framework. So users now would have the capability to actually go to this website, download the open source code. There's a development branch which contains the UHD support, And you can actually compile and run this software with any UHD supported devices. And we also have an example tutorial on our Cosmos Wiki page. And essentially, once the base station receives the pilot symbols on the uplink, it can use the received pilot sequence to compute channel estimation, basically to estimate the channel and compute the channel state information. And then it can also receive pilot, or it can also receive data packets on the uplink, and then compute the EVMs, SNRs, and some other relevant metrics. So I'm now going to go through some of these examples using a couple of demos. So we'll first do a CISO channel sounding tutorial using the two 2974s. So as you can see, so these are the two blue radios here in the sandbox. So let me switch to my terminal. So here we use one USRP with a single channel as the base station, and use another USRP 2974. So another USRP as a client, and we access both SDRs from the server. So essentially, we use the carrier frequency of 3.6 gigahertz. We're able to run a bandwidth of up to 100 megahertz using our servers. But in this demo, I'm going to do a lower bandwidth, just to ensure that there's no much conflicts on the Ethernet I'm using right now. So let me switch to my terminal. So here I have 3 windows open, as you can see. So Nilanjan already went through some of the basics of logging into the radio nodes. So essentially, I'm currently in the USB. I'll actually go through this very quickly. So essentially, you can log into the Sandbox tool console using the SSH command. And once you're in the console, you can see this huge Cosmos logo. And as Nilanjan and Mike mentioned, you can check the status of all the devices in the Sandbox too. So here I'm just running this command to check for all the status of the devices in Sandbox 2. As you can see listed here, we have the 4 radio nodes, which are all powered on and are going to be used by this tutorial. And we have the 2 servers on, which are also going to be used by this tutorial. And furthermore, we have these 2 RFDEV 2-1 and 2-2. So these are essentially the 2 IBM phased array antenna modules, which we'll be demonstrating in the second part of the tutorial. So now we have all the devices turned on. I can log into the server, which I plan to run my experiment on. So here I'm just SSH into server 1 large 1. So this is the first server of Sandbox 2. And once I'm in the server, one can essentially run UHD find devices and try to look for all the SDRs that are reachable from the Sandbox 2 network. So essentially, as you can see here, we see 4. So we can see 4 devices. So there are 2 N310s. So these are the devices 0 and devices 2. And there are 2 USRP 2974. So these are devices device 1 and device 3. So once all the devices are recognized in the network, we can actually run our software. So if you go to the link of the GitHub repository that contains all the code base, which we already downloaded on our local repository. So here we're just going to go into this directory that contains all the code. And essentially, one can already build the code, but you can just follow the guidelines on GitHub and then build the code. So once the code is built, there are a couple of files that configures the settings of different USRP devices. For example, if I open an editor, I can go to the file that configures the client. Right? So here, there's a file that configures clients, basically saying that I'm going to use the SDR number 2 on this IP address as the client, and then I'm going to set the front end gains of this device as these values. So the carrier frequency is 3.6 gigahertz. We're going to run a real-time bandwidth of 25 megahertz. Here, we're going to use a frame schedule, which basically transmits 1 pilot symbol on the uplink. That's indicated by this letter P here. So this is basically the setup for the client side. And here, since we're running a single channel, we specify the channel as using the channel capital A. And similarly, we can configure the specs for the base station. So here we use the same carrier frequency, we use the same single channel setup, and the same sampling rate or real-time bandwidth of 25 megahertz. And here, if you look at the frame schedule here, the first symbol B here represents the beacon the base station sends on the downlink. And then the letter P here means that once the client is synchronized with the base station is expecting to receive a pilot in this subframe. And here we also specify the IP address of the base station USRP in this file. So once everything is set up, we open 2 terminals. So we can run the client in one terminal and then run the base station in another terminal. So here, let's say on terminal number 2, I run the Sounder client using the configuration file USRP client only. So this is basically going to trigger all the interactions with the USRPs to set up the frequency, the front end, the antennas. And as you can see here, the client is expecting to receive a beacon from the base station. So that's where the status is in terms of the client. And now I'm going to run the base station. It's going to follow the similar command. I can just run the Sounder and use the configuration file as of a base station. So once this runs, you can see the similar steps that the server is trying to communicate with the USRP. And okay, let me stop this for now. So essentially what you're going to observe here is that we use HDF5 file format to record all the samples. And you can see the command here basically says that the base station starts the main receiving loop, and it's going to record these many frames on the uplink. So on the other side in the client, you're actually going to see there's a new line appearing here, which basically says beacon was detected as the specific timestamp on the FPGA. And then this is the synchronization offset between the downlink beacon and the uplink pilot. And once the client is synchronized with the base station, it's going to start its own transmission and receiving events on the uplink. So that's basically called after this start main loop command. So now we have all the samples recorded on the base station on the uplink. We can essentially run the Python script, which is also part of the ReneoLab software, to actually analyze the received samples on the uplink. So essentially, we go to this folder, which contains all the Python scripts, and we can simply run the script that plots all the samples with different metrics as part of the recorded HDF5 file. So here we just need to input the file name, which is the file that we just recorded. It's going to show up here. So this is the one that I just recorded. I believe it's 15. And then we're going to look at a specific frame, which is the frame number, let's say 1000. So once you run this frame and enable the XE11 tunneling, you're going to observe the received samples, right? So here, essentially, you can see in the top 2 rows, the recorded IQ samples in that selected frame, which is frame 1000. And in the middle 2 rows, you can see the aggregated received pilot across all the frames. So let's say if you zoom in here, you can see these are each of the chunks of the received pilots being recorded on the base station. So essentially, this shows the capability of doing the channel sounding on the uplink. And we can also do a similar thing in the MIMO setting. So essentially, let's open up the configuration files. And here, I'm gonna enable the client and base station to use both channels. So here, I just need to select channel A and B for the client. And here, I need to add another slot for the pilot. And similarly, for the base station, I'm gonna reconfigure the files of the base station and add another channel of B. And then also add another slot P here, where the base station knows where to receive the second pilot. So going back to the concept, so there's a difference between the CISO channel sounding and MIMO channel sounding. So here, in the case we're demonstrating here, the base station has 2 antennas, and also the client has 2 antennas. So the base station follows the similar procedure to keep sending beacons on the downlink. Once the client receives the beacon and synchronizes itself with the base station, it's going to schedule 2 orthogonal pilot sequence in 2 consecutive subframes or in 2 symbols. And here, pilot 0 will be sent from antenna 0 in 1 slot, where antenna 1 is not sending anything. And in the next slot, pilot number 1 will be sent from antenna 1, where antenna 0 will be sending nothing. And because of the defined TDD frame schedules, the base station now knows that it's supposed to receive 2 pilots in 2 consecutive frames. So this is essentially what we're doing here in terms of setting the frame schedules to be different values than in the CISO case. So that's why here, if you look at the frame schedule, there are 2 consecutive letters of P, indicating that there are 2 orthogonal pilots being sent from each of the client antennas. And on the base station side, the base station knows that in these 2 subframes, or in these 2 symbol slots, it's going to receive 2 pilot symbols. Okay, so once we're done with the configuration, we can follow the process and then run the Sounder client using the updated client configuration file, which contains 2 channels and 2 orthogonal pilot symbols on the uplink. So similarly, this shows the status where the USRP is actually enabling both channels with a given gain. And now, since we haven't started the base station yet, the client is looking for the downlink beacon to be synchronized with the base station. On the other side, similarly, we run the Sounder base station using the base station configuration file. And similarly, we have the IP address for the base station USRP. It initializes 2 channels, and it starts to send beacons and receive files and record the samples into this HDF5 file. And on the other side, you can actually see that here, a new line popped up, which basically indicated that the downlink beacon has been detected by the client. And once the client is synchronized with the base station, it's going to send the orthogonal 2 pilots from each of its antennas. So similarly, this file was recorded in the new HDF5 file format, and we can run the similar process to analyze this file. So essentially, we can run the same plot HDF5 script, and we point that script to these newly recorded files, which is named trace. Actually, 14-5. You can actually see the end here. The 2x2 here actually means the newly recorded 2x2 uplink sounding results. So here, since we have multiple antennas, we need to specify which antennas we're looking at. So here, let's say we look at ref antenna 0. This is the antenna number 0 at the base station. And we want to look at the pilot received from the first client antenna. So here, we just specify reference antenna to be 0 and also reference user to be 0. So this is essentially the channel 00 of this MIMO channel. And similarly, we look at a particular frame, which is the frame number 1000. And once we run this script, similar as before, we can observe the received uplink samples here. Right, so essentially, you can actually see this is the recorded pilot on the uplink, and also the concatenated samples from both channels. And here you can also see the recorded pilot from both users as well. So basically, this demonstrates the capability of running a real-time channel sounder. And people can also try to actually further enable the bandwidth. For example, in order to save time, I pre-recorded a trace file yesterday where we run a 50 megahertz channel. So for example, if we say, so this is the 2x2 channel matrix that I recorded from yesterday, and you actually see the real-time framework also supports real-time sounding and even data transmission at a real-time bandwidth of up to 50 megahertz. So for example, here we can even add uplink symbols from the client. So the first column here shows the received pilot symbols, and the second column here shows the data symbols. So all of these is part of the Renew framework software, which is open sourced on GitHub. If you look to the website, if you choose the development branch, you can get the version that also supports UHD, which has been demonstrating in this tutorial. And you can also find more details about how to run these experiments on the Cosmos website. So to summarize, in the MIMO channel sounding case, we have one USRP using dual channels, both A and B, as a 2 antenna base station, and another USRP 2974 using dual channels A and B to serve as a client with 2 antennas. And we can actually get the complete channel matrix, a 2x2 complex value channel matrix between the client base station. And one can further use other functionalities as part of the framework to, for example, send uplink pilots and then compute the corresponding SNR values, the EVM values, and things like that. So with that, I'd like to conclude this sounding tutorial. And if you look at the source code and the code base, it actually supports much more antennas. So essentially, we're planning to add more USG support so that this framework can actually support more than 2x2 MIMO sounding. Hopefully, we can run a small scale massive MIMO sounding testbed using USRP SDRs as part of the Cosmos testbed. And with that, I'd like to conclude my my tutorial, and I'll be doing a similar thing, but with the IBM 28 GHz phased array antenna modules after the coffee break.